If you work around industrial tilters, or you spec them, manage them, or maintain them, this video is for you. We're going to walk through the engineering and safety fundamentals that govern these machines, anchored in ANSI MH29.2, the recognized consensus standard for industrial tilter safety. This is not a certification course. It's not a sales pitch. It's awareness. Because too many incidents involving tilters come down to a gap between what the machine was designed to do and what the people around it actually know. Let's close that gap. So, what exactly is an industrial tilter, and what isn't one? Under ANSI MH29.2, a tilter is defined as a machine designed to rotate loads about a horizontal axis using hydraulic, pneumatic, or mechanical actuation. Maximum angular travel, 110 degrees. What is not covered by this standard? Lift tables, scissor lifts, dumpers and upenders with travel beyond 110 degrees. Inverters, truck-mounted dump bodies. Understanding scope is step one in safety planning. If your equipment falls outside MH29.2, a different standard or a full engineering analysis applies. Here's why tilters exist in the first place. Ergonomics. Workers accessing bulk bins, reaching deep, bending low, are putting themselves in the injury zone on every single cycle. Musculoskeletal strain is one of the leading causes of lost time injuries in manufacturing and distribution. Tilters solve this by repositioning the load into what ergonomists call the power zone, roughly shoulders to knees, where the human body handles material most efficiently and with the least risk of injury. Safe machine, safer worker, better throughput. That's the value proposition. Before we get into hazards and requirements, let's establish a shared vocabulary. A tilter has four primary components: the platform, the load-bearing surface, measured perpendicular to the hinged edge; the pivot axis, the horizontal hinge point around which everything rotates; and the actuator, the hydraulic cylinder, pneumatic airbag, or mechanical drive that creates the angular motion. Knowing these terms matters when you're reading a spec sheet, reviewing a risk assessment, or talking to a manufacturer about your application. Not all tilters are built the same, and the actuation system determines a lot about how the machine behaves under load and under failure. Hydraulic systems are the workhorse. High capacity, positive displacement pumps. Velocity fuses and relief valves preset to 125% of rated capacity. One specific caution: the fluid matters. Do not substitute synthetic hydraulic fluids that swell seals designed for petroleum bases. Pneumatic systems use compressed air and airbags. Self-lubricating, clean, non-invasive. Ideal for food-grade or pharmaceutical environments. Mechanical systems use drives and gears, but they carry a critical design requirement. They must prevent unintended movement if power is lost. That is not optional. It is engineered in. This is where engineering gets critical, and where a lot of field problems originate. Stability on a tilter is governed by something called the overturning factor of safety, the OFS. ANSI MH29.2 requires an OFS of at least 1.3 to 1. That means stabilizing moments must exceed overturning moments, including dynamic transfer forces, by 30% or more. Center of gravity is everything. For standard units, a static load center of gravity must stay within 20 inches above the platform and 20 inches from the backstop. Exceed those limits, and you are operating outside the machine's design envelope. Angular creep is another parameter to watch. System leakage must not allow more than 1% of maximum travel over 15 minutes under full load. Creep is normal. Excessive creep is a warning sign. Strength is not just about whether a structure holds. It's about whether it holds with an adequate safety margin. ANSI MH29.2 requires load-supporting elements to exceed ultimate material strength by defined ratios. 3:1 for ductile elements, 5:1 for non-ductile and flexible elements. Deflection is also mathematically bounded. Maximum allowable deflection equals L plus W divided by 64, calculated when 50% of rated capacity is placed on the furthest half of the platform, tilted to 30 degrees. Why does this matter on the floor? Because excessive structural deflection can shift load center of gravity unpredictably, and that directly affects stability.
Let's talk honestly about what these machines can do to a person if the hazards are not managed. As the platform moves through its arc, lethal crush and shear zones are created at the base of the frame, underneath the platform, and behind the platen. These are not hypothetical hazards. They are geometric certainties of how the machine operates. Load instability is a second hazard category. Unbalanced loads, shifting contents, or parts falling out if the platform rises too quickly. And unintended descent, hydraulic line failure or power loss, causing rapid, uncontrolled lowering, is a third. The standard addresses all three. Guards, velocity fuses, and control design exist because of what we just described. ANSI MH29.2 specifies 4 recognized guarding methods, each one designed to address the crush and shear zones we just identified. Bevel toe guards, 11-gauge steel, slanted inward at approximately 30 degrees. They push footwear outward as the platform descends. Minimum width, 8 inches. Skirts, accordion-style shields in metal or wood that completely block the exposed entrapment area. Toe sensors, electronic active guards. On contact, downward movement stops immediately. Maximum unguarded clearance below the platform, 7/8 of an inch. Fixed guard enclosures, solid or mesh fencing, up to 8 feet high or full tilt height, physically prevents access to the hazard zone. Mesh openings cannot allow a 2-inch sphere to pass through. Each method has trade-offs. The right choice depends on your operation, your workflow, and your risk profile.
Control interface design is where human behavior meets machine safety. And the standard has specific expectations. Press and hold controls are the baseline. The machine moves only while the operator maintains pressure and returns to the off state the moment it's released. Simple. Effective. Press and release enables automated cycles, but this introduces greater risk if something enters the hazard zone mid-cycle. The requirement? A highly accessible emergency stop device that immediately deactivates all powered functions. Slow. Highly accessible is not a vague term. It means reachable without repositioning the body.
On the system override side, relief valves are factory preset to prevent raising if a load exceeds 125% of rated capacity. Velocity fuses at cylinder ports arrest uncontrolled descent in the event of fluid loss.
Here's a mindset shift that ANSI MH29.2 builds into its structure. Safety is not one person's job. Manufacturers design to standard, overturning factor of safety, structural integrity, guarding. They provide warning labels, manuals, and specific center of gravity limitations. That documentation is not optional paperwork. It defines the machine's safe operating envelope. Owners and users match the tilter to the right environment, maintain it, train personnel, and advise the manufacturer of any unusual load shifts or dynamic forces. If your application changes, loads get heavier, load geometry changes, that conversation with the manufacturer is required, not optional. Operators execute pre-start inspections, maintain clear work areas, ensure load stability on every cycle, and refuse to operate malfunctioning equipment. That last point matters. Operators have the right and the responsibility to stop work. For owners and users, the standard translates to 3 practical obligation areas. Maintenance and inspection must be routine, frequency based on manufacturer recommendations, and operational severity. One specific caution: do not use synthetic hydraulic fluids that swell seals designed for petroleum bases. It is a common and costly mistake. Safe servicing requires a defined sequence before any adjustments. Remove the load. Relieve system pressure. Disconnect power. Lockout, tagout. And block the empty tilter with an approved maintenance device. Every step, every time. Documentation and repair. Manuals must be accessible to floor personnel. Parts must be manufacturer approved. A field substitution that seems equivalent can void engineering calculations and introduce new failure modes. Operators are the last line of defense and the first line of prevention. The 3-step pre-operation sequence is non-negotiable. Step 1. Pre-start visual test. Check for oil leaks, frayed wiring harnesses, loose casters or pivot pins, and verify that all warning decals, danger and warning, are legible. If a label is damaged or missing, that is a maintenance item before operation. Step 2. Load placement. Always center the load evenly and place it firmly against the backstop. This directly prevents shifting when the platform rises. Step 3. Workspace verification. Clearance from overhead obstructions. No electrical hazards. No unauthorized personnel in the tilt zone. 3 steps. Every cycle. No exceptions. The synthesis of everything we've covered comes down to 3 interlocking pillars. Engineered tolerances, the machine designed and built to standard. Active and passive guarding, the physical and electronic systems that catch what humans miss. Trained human protocol, the operator who knows the machine, knows the hazards, and acts accordingly. Remove any one of those 3, and the system fails. An over-engineered machine cannot protect against an operator who overloads the center of gravity. A perfectly trained operator is helpless against bypassed velocity fuses or removed toe guards. Safety is an integrated ecosystem, not a checklist you complete once. Everything in this video is grounded in ANSI MH29.2, safety requirements for industrial tilters, a consensus standard developed by engineers, safety professionals, and industry stakeholders to protect the people who work around these machines every day. This is not a substitute for the full standard, and it is not a substitute for your manufacturer's documentation. For comprehensive compliance, engineering specifications, and complete safety checklists, consult ANSI MH29.2 directly. Ensure all tilters in your facility are installed, anchored, and operated per factory specifications. If this was useful, share it with someone on your team who works around industrial material handling equipment. That's the point. Awareness travels.